Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the problem maximum width of a binary tree. Its index is 662 and it is the medium problem, the LeetCode. Given the talking about the prerequisites to solve this problem, you must know the concept of binary tree, and you should be aware about how you are going to perform breadth first search or depth first search to find out the maximum width of the given tree. Okay, so it is not a big deal. So you need to know how to iterate in a binary tree through some standard traversal methods like breadth first search or the depth first search. Okay, so let's begin. Given the root of a binary tree, return the maximum width of the given tree. Okay, so we need to return the maximum width of the given tree. So let's understand what is this term maximum width for a given binary tree. The maximum width of a tree is the maximum width among all the levels. That is, we need to consider all the levels, and we need to maximize the width by considering the width for with respect to every level and print the maximum answer. The width of one level is defined as the length between the end nodes, where the null nodes between the end nodes are also counted into the length calculation. Okay, so you need to consider the first node of a particular level and the last node of the particular level. Note that the the null nodes between the end nodes is also counted into the length calculation. That makes this problem quite interesting. So I will tell you how we are going to deal with all that stuff. So for now, let's look over the constraints for a bit. Number of nodes in the tree is going to be between 1 to 3000, right? So we are going to have a standard, we are going to have a apply standard breadth first search or depth first search. Okay, so for now let's understand what is the this problem is going to tell us about and how we are going to perform the operations efficiently. So so let's first understand the width of a level, and then our maximum width of a binary tree is going to be max of all the width of the level. Let's call this as wi. Will be w1, w2, and it goes up to wn for all the levels. Okay, so suppose we have been given this binary tree. Yeah, okay, suppose this is the binary tree we have been given to us. So so what we need to consider every levels. So let's start from the level equal to 1, that is only this node, and for level equal to 2, that is for this one, for level equal to 3 for this one, and for level equal to 4 this one. Now we need to also consider the null nodes. So so how we are going to deal with that? So you can see there is not any null node, like there doesn't exist any node over here. So we will insert an imaginary null node for understanding purposes. Okay, null node, and here also would be having the null nodes. Okay, and we can have this null node over here, we can have this null node over here, and we can have this null node over here and null node over. I think we are done. Okay, so how do we find the width of a particular level? So you can see there exists only one node at this level equal to 1. Okay, so width of a particular level would be the distance between the end non-null nodes. Okay, the distance between the end non-null nodes. So if you're at this level 1, you can see there exists only one node. So our distance d would be, okay, so distance plus 1 actually. Okay, so this will be at position 0. Okay, so you will say a starting node would be, let's say a starting node would be at position 0, and ending node will also be at position 0, because there exists only one node. So distance would be e minus s plus 1, so it would be 1. So width of this particular level would be 1. So let's write down w1 as 1. Okay, so now let's consider this position. Okay, so you can see there exist two nodes. So this is the imaginary edge I have been added, but it doesn't mean anything like these both are connected. So, okay, so for now let's understand with this one. So this is at position 0, this is at position 1. So the distance between the end non-null nodes, these two are non-null nodes. So my W2 would be 1 end minus S, which is the position starting node, plus 1, which is actually 2. So W2 would be 2. Okay. And similarly, let's consider for this part. Okay. So you would say like we have this node and we have a null node, and again we have this non-null node, and again we have this null node. Okay, so how do we find the distance? You can see distance is actually the between the non-null nodes, end nodes. Like this is non-null node, the very first node, and the very last non-null node with this one. So position is 0, 1, 2, 3. So W3 would be end, which is 2, like end non-null node, and start non-null node, 2 minus 0 plus 1, which is actually 3. So W3 would be 3. Note that you need not to consider this null node, because this is not the last non-null node. Right, right. This has been drawn for the imaginary purpose to understand. Since we need to account for the null nodes also between the two end nodes, that's why I have drawn these null nodes. Okay, so now let's understand for the next level, that is for this one. Okay, so let me just erase some of the parts. Okay, right. Now we are talking about this position. Now we have this null node, and then again we have non-null node, null node, null node. So this is the first non-null node. So its position would be actually 1. Its position is 0. Its position is 2. Its position is 3. And what is the last non-null node? It is again this one. So my W4 would be 1 minus 1 plus 0, which is, sorry, 1 minus 1 plus 1, which is actually 1. So W4 would be 1. So what is the max of all these values, which is 3. So 3 would be our answer. Okay, so how do we maintain the entire thing? Like suppose there exists some null node, then how do we find out that correct positions? Like if you are talking about this one, this level, you can see this node has the position 1, and this node has the position 3, right? If you consider one based positioning, so its position is 1 and its position is 3, like actual position by considering null nodes. So you can find out these positions simply by giving some IDs to each node, and the ID would be something like this. Suppose we have this binary tree, so you will give the ID as 0 for this one, and whenever you move to the left child you will do ID into 2, and whenever you move to the right child you would do ID into 2 plus 1. Okay, and again if you are at this position, like if you are moving from this to this, your current ID is this one, so you will do ID into 2, which is the previous one, into 2, like you're moving to the left child. And when you're moving to the right child you will do ID into 2 into 2 plus 1, this is for the previous one, into 2 for the current, and plus 1 would be since you are moving to the right child. And when you go to this one you will do ID into 2 plus 1, which was for the previous one, you can see, and into 2 plus 1 since you're moving to the right child. Okay, so let us find out the IDs for this given binary tree again by numbering. Okay, so there is a null node over here, imaginary, so you can see I will position it as 0, 1, 2, sorry, so this would be like 0 and this would be like 1, and again 0, 1. Since null node should also be considered, its position would be 2, its position would be 3, right? So let's find out through this method, like whether it is giving the correct answer or not. You can see if I'm moving to the left child, 0 into 2, which is again 0, and if we are moving to the left child, 0 into 2, which is 0. When you're moving to the right child, 0 into 2 plus 1, correct one, and 1 into 2 plus 1, 3, which is correct. And again, if you're at over here, you're moving to the right child, then yeah, you would be having 0 into 2 plus 1, which is actually 1. So all the values are correct. Okay, so this is what you're going to do with respect to positioning. Okay, so let's try to code it out how we are going to do that. And yeah, there would be some runtime error also if you do not consider this condition. Like suppose you have this skew tree. Skew tree is nothing but a linear mapping of the nodes, you can also say, like this part. Okay, so you can see max number of nodes is around 3000. Like if you have this type of skew tree and n is around 3000, so whenever you move to the right child, you have id, like so initially your id is 0, so 0 into 2 plus 1, which is 1, 1 into 2 plus 1 is 3, and here you'll be having 7, 15, 31, and so on. So you can see if n is 3000, it will overflow, the value will overflow. Okay, so yes, we can handle that also, but for now let's understand how we are going to replace. Like if you're using int, then it will give you a runtime error, and if you will use unsigned int, then it will give you all correct. But using unsigned int is quite like you're not aware about that this will pass, so I will tell you how to set the offset value for every level. So for now let's understand how we can code it out using the unsigned int part. So yeah, you can see I have a runtime of 0ms solution. The time complexity will be open and space complexity will be also open, because we are going to use a queue performing breadth first search. Okay, so yeah, so I would be taking a pair queue of tree node, that is the current root node, and its id, which is of type unsigned int. If you use int, you will get a runtime error as I received over here. So okay, so it's pushing the root node and pushing its id as 0. So unsigned int answer, which is the maximum width of the given tree, initialize with 0. So I will iterate for all the levels. You can see first I will find the size of this queue and extract all the nodes present on the current level, and this f and s are basically the first node and the last node for the given level. So initialize with -1. So extracting the nodes of the current level will be done like this one. Extract this node and extract the id of the current node and extract the node's address. Okay, so if f is still -1, then I will assign f as the current id, that is the very first node, and s will be the final id of the node of the current level. Also you need to, if you are moving to the left child node, you will do id into 2. If you will move to the right child node, you will do id into 2 plus 1. Now our answer will be max of the first node, max of the difference between s minus f plus 1. Okay, this will give you all test cases passed. But you know, the idea of coming with unsigned int is quite difficult. So what we are going to do is we are going to set some offset level for offset value for every level. So I have written the code also. I have the code, which is, you can see everything is quite similar. I'm taking the int, but you can see I'm finding using this offset as the first node of the current level, which is actually the minimum value of the current level, and I will be finding the difference between the current id of the node and the offset value for each level, and then I'm pushing the new value, which is d into 2 if you are moving to the left child node, and d into 2 plus 1 if you are moving to the right child node. Okay, so what is the idea behind that? So let's understand. So you can see for a current level, for a level, you can see our answer is like current answer is actually maximum ID minus minimum ID plus 1, right? So it may happen like you can see in this skew tree, right? In this tree, this value, maximum value, is going to be like very much large, right? And minimum value is also going to be very much large, so it may overflow. So we can write this term as you can see max minus some offset value minus min minus some offset value plus 1. So this is actually the current answer. If we are able to write like this type, then we can like we are done. So you can see this offset value must be the minimum value of the current level, because if it is not, then minimum minus offset will become negative and this entire relation will be corrupted. So this offset is going to be exactly equal to the min value for the current level. Okay, so you can see if you simplify this equation, you will get the same equation as it is over here. So we can write this current answer in this form. So if you are able to do that, then we can have the new values, which is d, which is actually the current id minus offset value, and offset value is nothing but the minimum value of the current level, minimum id. Okay, so this is what I'm going to do. Offset will be set to the minimum id, and each when we extract the node, we'll find out the new value, which is d. And again, yes, moving to the left one, d into 2, moving to the right one, d into 2 plus 1, and everything remains same. Okay, so you will get all test cases passed. So if you guys have still any doubts, do reach out to us through the comment section of the video, and thank you for watching this video.